There's a city in southern Italy where the ground underneath people's feet is moving upward, not shifting, not settling, rising. Since 2005, the earth beneath the western edge of Naples has climbed more than 1.6 meters vertically. That is over 5 feet of measurable, documented, relentless geological ascent across an entire urban landscape. Then, in June 2025, the region absorbed the most powerful earthquake ever captured in its entire modern scientific monitoring history. A magnitude 4.6 event that rattled buildings, cracked infrastructure, and sent tremors through a population already living at the edge of a geological emergency. And what makes this genuinely terrifying is not the single earthquake. It is that the earthquakes are not pausing between events. They are not settling into a rhythm. They are compounding, accelerating, intensifying in a pattern that researchers now describe mathematically as super exponential growth. A peer-reviewed model published in 2026 ran the numbers forward and arrived at a projection that stopped the scientific community in its tracks. If the current rate of uplift holds, the ground could rise by a total of 4 meters above its baseline by the early 2030s. That would be a geological state with no modern precedent in the recorded history of this structure. And the structure responsible for all of this is not Vesuvius. It is not the mountain everyone pictures when they think of Naples. It is something far older, far wider, far more powerful, and almost completely invisible to the untrained eye. It is what Italians call Campi Flegrei, the Phlegreian fields, and it is a 12-kilometer-wide supervolcanic caldera with 500,000 people living directly on top of it. The reason most people have never heard of Campi Flegrei is because it does not look like what people expect a volcano to look like. When the word volcano enters a conversation, the human brain conjures an image: a mountain, a cone, a summit, a crater at the top, the silhouette of Vesuvius rising above the Bay of Naples, unmistakable and monolithic. Vesuvius is exactly that. It sits east of Naples, visible from virtually every elevated point in the metropolitan region, a geological monument that has defined the skyline and the cultural imagination of southern Italy for millennia. The 79 AD eruption that buried Pompeii and Herculaneum has made Vesuvius perhaps the most narratively famous volcano in human civilization. Everyone knows its name, everyone knows its shape. That familiarity creates a dangerous psychological distortion because it implies that the volcanic threat facing Naples is located on that mountain to the east. It is not. At least, it is not exclusively. Because directly to the west of Naples, in the opposite direction from Vesuvius, lies something that defies every visual expectation of what a volcano should be. Campi Flegrei does not rise above the landscape. It is the landscape. Where Vesuvius is a stratovolcano, a single, towering conical edifice built from layers of lava and ash accumulated over hundreds of thousands of years, Campi Flegrei is a caldera, a depression, a geological bowl 12 kilometers across, formed not by the slow accumulation of material, but by catastrophic collapse. When a volcano of sufficient scale empties its magma chamber in a single cataclysmic eruption, the ground above the emptied chamber has nothing left to support it. The surface collapses inward, sinking into the void left behind, forming a wide, shallow depression that can be tens of kilometers across. That is Campi Flegrei. The towns built inside it, Pozzuoli, Boccoli, Monte di Procida, and the sprawling western neighborhoods of Naples itself, sit inside the remnants of collapsed ancient eruptions, without any visible evidence that they are living inside a volcano at all. There are vineyards there. There are coastal promenades overlooking the Tyrrhenian Sea. There are hilltop vistas, thermal springs, Roman archaeological sites, fish markets, and beachfronts. The landscape is strikingly beautiful, and, from any ordinary vantage point, gives no suggestion of the geological machinery operating beneath it. Approximately 500,000 people are permanent residents inside the caldera boundary. The broader Naples metropolitan region adds several 100,000 more in the immediately surrounding areas. These are not remote rural populations. These are dense, urban, modern communities, living inside an active supervolcano that is, right now, in real time, in a documented state of accelerating geological unrest. To understand what Campi Flegrei actually is, and what it is capable of, you have to go back not decades or centuries, but tens of thousands of years, to the events that created the structure in the first place. Approximately 40,000 years ago, Campi Flegrei produced one of the largest volcanic eruptions documented anywhere on Earth in the entire period of human existence. This event is known as the Campanian Ignimbrite eruption, and its scale is staggering even by the standards of geological catastrophe. It registered a 7 on the Volcanic Explosivity Index, a logarithmic scale where each unit represents a 10-fold increase in ejected material, placing it among the most powerful eruptions in the archaeological record of the human species. The eruption expelled roughly 200 cubic kilometers of volcanic material. To put that in proportion, the 1980 eruption of Mount St. Helens in Washington state which killed 57 people, flattened entire forests, and reshaped regional geography, ejected approximately 1 cubic kilometer of material. The Campanian ignimbrite eruption produced 200 times that volume. The ash cloud from that single event spread across the entirety of the European continent, across Russia, across portions of North Africa. Geologists can identify the chemical signature of the Campanian ignimbrite in sediment cores pulled from the floor of the Mediterranean, from lake beds in Eastern Europe, from ice deposits far to the north. Some researchers studying the extinction timeline of Neanderthal populations across Europe have noted that the collapse of those populations in the archaeological record correlates temporally with the climatic disruption that would have followed an eruption of this magnitude. The causal relationship is not scientifically settled. The debate continues. But the timing is not coincidental, and the scale of the environmental impact on late Pleistocene Europe was unambiguous. Then, approximately 15,000 years ago, Campi Flegrei erupted a second time in a caldera-forming event. This eruption, smaller than the Campanian ignimbrite but still catastrophic on any regional or continental scale, produced what geologists now call the Neapolitan yellow tuff. The distinctive pale yellow volcanic rock deposited during that eruption became the literal building material of Naples. The churches, the palaces, the catacombs, the ancient walls of the city, much of it is physically constructed from the compressed ejecta of a volcanic cataclysm that reshaped the landscape 15 millennia ago. The caldera collapsed again following this event, deepening and widening the depression. The landscape that humans eventually settled, the fields, the harbors, the hills, was shaped entirely by these two acts of geological destruction. This is what places Campi Flegrei in a category that most people do not know exists. The same classification that applies to Yellowstone in the western United States. The same classification that applies to the Toba caldera in Sumatra, whose eruption 74,000 years ago may have reduced the global human population to just a few thousand individuals. The same classification that applies to the Aira caldera in southern Japan. Campi Flegrei is a documented supervolcano, a caldera system capable of producing eruptions of a magnitude that can alter regional climates, collapse civilizations, and leave permanent marks in the geological record of multiple continents. The difference between Campi Flegrei and Yellowstone, the comparison that scientists return to again and again, is not geological. It is demographic. Yellowstone sits beneath a wilderness. Its nearest significant population centers are hours away. A catastrophic eruption at Yellowstone would be a global event, but it would not erupt directly beneath dense urban infrastructure. Campi Flegrei would. The eruption zone is the city itself. And here is the fact that transforms this from a geological curiosity into a present-day emergency. In 1538, Campi Flegrei erupted. Not metaphorically. Not in the abstract geological timescale of tens of thousands of years. In the year 1538, within the recorded history of Western civilization, within decades of Columbus reaching the Americas, within the lifetimes of figures history still remembers, this supervolcano opened a new vent, built a new mountain out of the earth, and violently reminded the people living inside the caldera that the system beneath them was not finished. And the sequence of events that preceded the 1538 eruption is the sequence of events that geologists and volcanologists are watching replicate itself with modern precision and modern instruments right now. Before 1538, Campi Flegrei had been geologically quiet for approximately 3,500 years. The entire Bronze Age passed without a major eruption. The Iron Age passed. The Roman Republic rose, conquered most of the known world, and fell, all while Campi Flegrei sat in geological silence. Roman engineers, with characteristic confidence in the stability of the landscape, constructed temples, harbors, bath complexes, and civic infrastructure directly across the caldera floor. The archaeological site at Pozzuoli, known as the Temple of Serapis, actually a market complex despite its popular name, preserves the physical evidence of those quiet centuries in its stone columns, which show the biological boring marks of marine mollusks at mid-column height, indicating that portions of the structure had at various points subsided below sea level and then re-emerged. This is the geological oscillation of a caldera system, breathing slowly over centuries. Then, sometime in the early 1400s, the breathing changed. The ground began to rise. Slowly initially, slowly enough that the communities of the time would have had no conceptual framework for what they were witnessing, and then with increasing momentum over the following decades. Modern geodetic reconstruction of that pre-1538 uplift episode, using the biological and archaeological evidence embedded in ancient structures like the Temple of Serapis, has established that the magma source responsible for that 16th century unrest is the same magma source that is driving the current unrest. Same plumbing, same chamber, same geological engine, which activated more than 600 years ago, built pressure for over a century, and eventually forced its way to the surface. In September of 1538, a new volcanic vent tore open in the western portion of the caldera. Over the course of approximately 1 week, that vent constructed a cinder cone 130 meters tall from raw volcanic material. The Italians named it Monte Nuovo, the new mountain, and it is still there today, a small forested hill visible from the hills of Pozzuoli, a permanent monument to the last time the system broke through the surface. The eruption was modest by Campi Flegrei's historical standards. The volume of material expelled was a fraction of what the caldera-forming events produced. But modest does not mean harmless. Multiple villages in the western caldera were obliterated. The population of Pozzuoli fled, people died, and what followed the Monte Nuovo eruption was not ongoing volcanic activity. The system went quiet again. Which raises the question that every volcanologist studying Campi Flegrei carries with them into every meeting, every model run, every data review. Is the current unrest episode the slow, century-scale precursor to another Monte Nuovo, or to something much larger? The current unrest episode at Campi Flegrei began in 2005. It is now in its 21st consecutive year. Every single year since 2005, the ground above the magma chamber has been rising. Every single year, the seismic activity has increased. Every single year, the geochemical signals from the volcanic gas emissions have shifted in ways consistent with increasing magmatic pressure from below. 3 previous unrest episodes occurred at Campi Flegrei in the modern monitoring era. Between 1950 and 1952, between 1970 and 1972, and the most alarming episode before the current one, between 1982 and 1984, when the ground rose by nearly 2 meters in under 2 years, and the Italian government ordered a partial evacuation of Pozzuoli. All 3 of those episodes eventually subsided. The ground stabilized, the seismicity dropped, the system retreated. The current episode has not retreated. In 21 years, it has not produced a single year of measurable stabilization. The cumulative uplift across all 4 episodes since 1950 now exceeds 4.3 meters. The current episode alone accounts for more than a third of the total, and has produced the 2 largest earthquakes ever recorded at Campi Flegrei in the modern monitoring era, magnitude 4.4 in 2024, magnitude 4.6 in June 2025. These are not random fluctuations. They are data points on a curve, and the curve is pointing in one direction. Researchers at the GFZ Helmholtz Center for Geosciences in Germany, working in collaboration with Italy's National Institute of Geophysics and Volcanology and the University of Pisa, published a landmark study in 2026, examining the relationship between the ongoing ground deformation and the seismic activity it is generating. Their findings revealed something deeply unsettling. The earthquake rate is not simply tracking the uplift rate on a linear, one-to-one basis. The seismic response is disproportionate. It is accelerating faster than the deformation alone would mathematically predict. The relationship between ground movement and earthquake generation has become nonlinear, suggesting that the structural integrity of the upper crust beneath the caldera is changing. The rock is responding differently to the same pressure than it did at the beginning of the unrest episode. Separate seismic analysis has identified what researchers describe as fluid-filled crack-like structures forming in the shallow crust beneath the caldera floor. These are not ancient features. They are being created now by pressurized fluids, magmatic gases mixing with the extensive groundwater system heated by the magma below, finding new pathways through rock that was previously intact. Every new fracture is a modification to the structural architecture of the caldera's upper crust. Every new pathway for pressurized fluid is a redistribution of stress inside a system that is already under enormous geological strain. Gas emission data from Solfatara crater, the most geologically active surface feature in the caldera, and a site of continuous fumarolic activity for centuries, has shifted in chemical composition in ways that volcanologists interpret as evidence of increased magmatic gas contribution from deeper in the plumbing system. The carbon dioxide to sulfur dioxide ratios, the helium isotope signatures, the temperature gradients at individual fumarole vents, all of these measurements are trending in the direction of a system with growing connectivity between the deep magma source and the surface expression of the volcano. A statistical modeling paper published in March 2026 by Zaccagnino and colleagues applied rigorous mathematical projection to the current trajectory of the unrest. They did not speculate. They ran the documented trend lines forward and arrived at a specific quantified threshold. If the rate of ground uplift measured between 2005 and 2025 continues without deceleration, the total cumulative uplift at Campi Flegrei could approach 4 meters by the early 2030s, within the current decade, within a time frame that is not geological abstraction, but lived human planning horizon. The researchers were careful and precise in their language. They were not predicting an eruption. They were identifying the point at which the system would enter a state of unrest with no direct precedent in the modern scientific record. 4 meters of total uplift would exceed every documented episode in the monitoring era. It would put Campi Flegrei into geological territory that existing historical data cannot fully characterize. For the 1538 eruption comparison, the pre-eruption uplift over that 130-year precursor period is not perfectly reconstructed. The measurement tools of the 16th century were not seismometers and GPS arrays, but the paleological and archaeological evidence suggests the cumulative ground deformation was substantial. The current episode is 21 years old, has produced 1.6 meters of measured uplift, and is accelerating. If the rate holds, the system could produce another 2 to 2.5 meters of additional uplift in the next 7 to 10 years. The 2030s are not a distant horizon, they are a planning window. What would an eruption at Campi Flegrei actually mean for the people inside the caldera? The range of possible outcomes stretches across an enormous spectrum. And where any future eruption might land on that spectrum is precisely the uncertainty that makes the current monitoring effort so critical. At the lowest end of the spectrum, an event comparable to Monte Nuovo in 1538, the immediate destruction would be concentrated near the new vent location. Pyroclastic density currents, which are superheated mixtures of gas, ash, and fragmented rock that travel at speeds of hundreds of kilometers per hour and incinerate everything they contact with temperatures exceeding several hundred degrees Celsius, would affect the vent proximal areas within minutes of any eruption beginning. Pozzuoli, which sits directly above the historically most active portion of the caldera, would face that threat first and fastest. The margins of response time in a pyroclastic event are measured in minutes, not hours. Ashfall from even a moderate eruption would affect Naples, potentially grounding air travel across southern Italy, contaminating water supplies, collapsing buildings under accumulating weight, and creating respiratory emergencies across the metropolitan population. Volcanic gas emissions, particularly sulfur dioxide and carbon dioxide, both of which are heavier than air and accumulate in low-lying areas, would create acute toxicity risks in valleys, basements, and underground infrastructure. At the higher end of the spectrum, an eruption approaching the scale of the Neapolitan Yellow Tuff event 15,000 years ago would produce pyroclastic flows capable of overrunning not just Pozzuoli, but most of southern Italy. The ashfall footprint would extend across the entire Mediterranean basin. Climate effects from stratospheric aerosol injection at that scale would be measurable across Europe, North Africa, and beyond over a period of years. The global economic disruption from a sustained climate-forcing event originating in a major European population center would cascade through every interconnected system of modern civilization. The scientific consensus holds that a caldera-forming eruption in the immediate future is a low-probability event. The precursor indicators that would typically precede a truly catastrophic caldera collapse eruption have not yet reached the thresholds associated with that outcome. But a smaller eruption, one closer to the Monte Nuovo category, sits within the current probability envelope as a scenario that the data does not allow scientists to dismiss. Italy is not passive in the face of this threat. The National Institute of Geophysics and Volcanology operates one of the most technically sophisticated volcanic monitoring networks on Earth, deployed specifically to watch Campi Flegrei. Dense seismic sensor arrays record every tremor, every micro-earthquake, every subsurface fluid movement that generates a detectable ground vibration. A GPS network covering the caldera measures ground deformation in real time, with precision sufficient to detect millimeter-scale changes in surface elevation. Gas chemistry stations at multiple fumarole sites track the molecular composition of volcanic emissions continuously. Thermal imaging systems monitor temperature gradients across the hydrothermal areas of the caldera. Satellite radar interferometry provides independent deformation measurements from orbit, cross-validating the ground-level GPS data. All of this information flows into a continuous analysis pipeline staffed by experienced volcanologists whose specific professional mission is to detect the earliest possible warning of escalating eruptive precursors. Italy's civil protection framework operates a 4-tier alert system for Campi Flegrei. The current level is yellow, the baseline designation for documented active anomalous unrest, indicating continuous monitoring is warranted. An elevation to orange would signal growing concern about potential pre-eruptive processes. Red alert would initiate evacuation planning and population movement. Evacuating 500,000 people from a dense urban environment built inside a caldera across road networks that serve a major southern Italian metropolitan region and that, on any ordinary weekday, operate at or near capacity, represents one of the most complex and logistically demanding civil protection scenarios any government agency on Earth has ever been asked to plan for. The geography of the caldera itself constrains evacuation corridors. The demographics of the population, elderly residents, mobility-limited individuals, tourists, workers, add layers of operational complexity. The margin between adequate warning time and insufficient warning time in the event of a rapidly escalating precursor sequence is a calculation that Italy's civil protection authorities are actively working to define. The critical operational question, the one that keeps volcanologists awake, is whether the monitoring network will be able to distinguish an accelerating pre-eruptive sequence from an intensified but ultimately non-eruptive period of unrest in time to move 500,000 people to safety before the volcano acts. The 1538 eruption was preceded by detectable ground deformation, by anomalous fumarolic behavior, by shallow felt earthquakes in the days and weeks before the vent opened. The populations of the 16th century lacked any instrumented monitoring system capable of quantifying those signals in real time. They experienced them physically, through the shaking of the ground and the smell of volcanic gases, and many did not leave in time. The technology available to Italian scientists today is incomparably more capable than anything that existed in 1538, or in 1984 for that matter. The instruments are more sensitive. The data processing is faster. The models are more sophisticated. The communication infrastructure to move a warning from a research institute to the phones of 500,000 residents is immediate. The question that remains unresolved, and that no amount of technological sophistication can fully pre-answer, is whether the physical behavior of the volcano will provide a sufficiently long and sufficiently unambiguous precursor window to translate monitoring data into a safe evacuation. Previous caldera systems around the world have produced eruptions with very short precursor windows. Others have produced years of accelerating unrest before eventually erupting. The history of Campi Flegrei itself includes 3 modern unrest episodes that never culminated in an eruption. The system has a documented capacity to build to alarming levels of activity and then retreat. But the current episode is longer, larger, and structurally different from those 3 predecessors in ways that researchers have been unable to dismiss as analogous to the episodes that quieted without incident. What is unambiguous is this: Campi Flegrei is one of only a handful of confirmed supervolcanoes on the surface of the Earth. It has produced 2 eruptions in the top tier of documented geological violence, events that reshaped the European landscape, affected global climate, and may have altered the trajectory of human prehistory. The last time it erupted, in 1538, it did so after more than a century of escalating unrest that began with the same geological signature, the same magma source, the same rising ground, the same pattern of increasing seismic energy that scientists are measuring today. The current episode began in 2005. It is in its 21st year. It has not paused. It has not stabilized. The largest earthquakes in the modern monitoring record occurred in 2024 and 2025. A peer-reviewed 2026 projection places the system on a trajectory toward a level of unrest unprecedented in the modern scientific record by the early 2030s. 500,000 people eat breakfast inside the caldera every morning. 500,000 people walk streets that have visibly tilted. 500,000 people live above Roman harbor infrastructure that has been lifted out of the sea by a magma chamber that is still rising. And the Mediterranean world goes on largely unaware that the most geologically consequential structure in Europe is not a distant wilderness or a museum exhibit. It is a living city, vibrating, cracking, lifting, and watched by scientists who understand exactly what they are looking at, and who cannot yet tell you what it is going to do. The data points to the 2030s. The geology points to a system already deep in unrest. The history points to a pattern that has played out before and ended in fire. What it cannot tell you, what no model, no instrument, and no monitoring network on Earth can currently answer with certainty, is whether the next chapter of Campi Flegrei's story ends the way the last one did, or whether the next eruption inside that 12-kilometer caldera is the one that changes the map of southern Europe forever. And 500,000 people are going to wake up inside that question tomorrow morning, the same way they did today, and the same way they will again, until the day they do not.